Okay, thank you. So I will insist a little bit on the slices. So instead of the proof, now I want to explain a little bit the theorem. So essentially, what's a slice? A slice is a set that, for convenience, I will put in the Zariski tangent space. Well, in the first cohomology group, and we'll see what this cohomology group means later. And it has two properties. First one is that the Zariski tangent space uh, is the whole cohomology group when the variety of representations is smooth. Not the variety of characters, the variety of representations is smooth. Then S is just an open subset. Yeah? And people call it analytic germ to say just an open subset here. But if it's singular, it's smaller. But the Zariski tangent space is everything. And I have a J equivariant map from this twist product to neighborhood of rho in the variety of representations, which is G saturated. G saturated means that it's close by G orbits. Yeah? Gx by conjugation. Yeah? So I want to understand the space of conjugacy classes. So Gx by conjugation, and this acts in the space of G orbits. And well, what is telling me the slides is that essentially I have to understand the variety of representations, and neighborhood is this twist product. Twist product means that this acts on the right and this acts on the left here, and I take the quotient. Yeah, and that's G times S divided by the action of G rho. If the stabilizer is trivial, it's just the product, okay? And the theorem that I sketch is that every representation has a slice. Every semi-simple representations, because again, we are interested in the good ones, which are the semi-simple guys. And this, as a conclusion of this, is that there is a nice B-analytic structure. Well, this analytic structure is unique at 2G row equivariance, and in the quotient when the representation is semi-simple. So I will show an example, but of the following color, one of the following colors, I don't remember which one, the first one, yeah, or the first corollary that says that this gives me a restriction of the homeomorphism. But a homeomorphism says that it's the slice divided by G rho, yeah? Because this is what this is G times G rho of S. You divide it by G. Well, the action should be on the other side, sorry. You divide it by G by conjugation, and that's this object, yeah? And this is the GIT quotient. GIT means that it's not a topological quotient because the topological quotient will be non-Hausdorff. So we remove the bad guys, the things that accumulate to identity and so on. I will show right now in an example what is this, okay? Another consequence that I will not give in this example, but it's very useful, is the representation is C-reducible. And C-reducible, that means that there is no invariant, rho invariant subset in Cn, yeah, which is Rn tensor C. Yeah, and perhaps then is the wrong n. Yeah, sorry, it's a small n. Oops. Okay, so let's jump to the example. And this is an example we saw before today, and it's the cyclic abelian group divided into SL to R, and we said that the quotient is that guy. Yeah. Here we had representations that correspond to rotations, in fact. Yeah? Matrices of rotations, that the conjugation is this, and this corresponds to diagonal representations. with positive eigenvalue, with negative eigenvalue. Yeah? Here you have the identity, the trivial representation, and here you have minus the identity. And here you have a rotation, where it's in red. And this is the space of conjugacy classes, and we saw that it's not trivial to compute this guy. Yeah, it's a semi-analytic set, and we saw how to compute it in the other example. Yeah, with equations and so on. Okay. What I want to explain now is that the character of the trivial representation is a trivalent vertex. Yeah, a trivalent vertex means is that it's here. This is the trivial representation, and it has three vertices, one here, and one here. Why is this? Yeah? Why is this? How do we use the slides to check this? Yeah? With this corollary I just marked before. Well, first item, the variety of representations is equivalent to G. Yeah, because it just map an element. So I didn't write here, but this was before. Said G, this is just G. Yeah? Just map any representation to row of one. This we said before. Second step is that, well, this cohomology at the trivial representation is just G. Yeah. So Z1 at the trivial representation is G. Yeah, just and B1, this co-boundary space, that's this is zero. Because the action is trivial, and this cohomology group is G. So let's see how this works. So the slice theorem tells me that the slice is just a neighborhood of the origin in the Lie algebra. Yeah, G equals SL to R. Okay, that's okay for the moment. So let me take the quotient. So the corollary says that, well, I have to take this G invariant quotient. So a neighborhood of the origin in here by SL to R. Yeah. Well, and what is amazing is that this quotient is a triplet graph. So you take SL to R, you take the action by the Lie algebra, you take the action by the Lie group, yeah, by conjugation, not just the quotient, but the GIT quotient. So you remove the bad guys, the orbits that accumulate to zero, the non-closed orbits, and you take the quotient of this. That's a trivalent graph. And that's what I want to explain in the next slide, that this is a trivalent graph. Okay, and this is what I wanted some time to explain this systems. So first thing, well, this is acting by conjugation. In fact, this is SL2R is the same as the action is the same as the action of SL2R. And this action is equivalent to the action of the group SO21. This is the component of the origin. So these are matrices that preserve the product 1, 1, minus 1. Yeah. This is because this is the same thing as R3, but you can say this is R21 because the killing form has signature 2-1. Okay. In fact, if you think of infinitesimal translations and infinitesimal rotations, there are many things to say that. So the first thing that you need to work out is that this action is equivalent to that one, if you want to understand this quotient. Yeah. And then I make this picture here on the left, because this corresponds to, well, here we have an axis which is Z, another axis which is X, another axis which is Y. And these are the level set of the quadratic form X squared plus Y squared minus Z squared. So this action, well, and this you can write it in the Lie algebra, but it's just working here. Yeah. We want to compute this quotient. So first thing that people do in geometric invariant theory, real or complex or whatever, is remove the orbits that are not close. And here there is an orbit which is not close, this one, because this one, if you take this light cone, this is accumulating to zero. To the origin. Okay? Why? Why it's accumulating to the origin? Well, it's accumulating to the origin because, well, I don't know, the orbit is everything minus the origin, so it's accumulated to here, yeah? So you remove that guy, okay? Here I forgot what equals to 0. Sorry, I forgot something. There is a typo. Now this has 3 components. It has 3 components. One component which are inside the light cone. I don't remember if they are time or time vectors, positive time, negative time. These are 2 components, and the third time component is outside. And in fact, this group acts transitively on each component on each level set. Yeah? Each component of the level set, I should say, okay? So this gives me the 3 axes, yeah? Because if I write, and I put it in black and thick, one axis is here, one axis is here. So this corresponds to each orbit. One axis is here. This corresponds to the other orbits. And one axis is here. This corresponds to the other orbits, yeah? So each orbit, so the orbits of this hyperboloid with one leaf, each level set meets this one in only one point. Each upper leaf meets these edges in just one point, and each lower leaf meets its edges in just one point. And the result, the final quotient is, well, and I have, of course, I have the origin too, which is here. Yeah. And this is why this quotient is a non-algebraic, is a semi-analytic, non-algebraic set, but it's just a semi-algebraic set, okay? And well, I put an exercise. Well, you can think it's an exercise or not. The minimal quotient, or the minimal set of Richardson and Slobody for the Euclidean norm. So you realize that on each leaf like here, there is only one point that minimizes the length. It's this point. And this point, and here the action of SO2 is trivial. Same thing in the lower leaves. So each leaf, there is only one point that minimizes the distance. And for the exterior leaves, so for the cedar leaves, these ones, there is a whole circle that minimizes the distance. Okay, it's just circle. This minimizes the distance of the leaf of the origin, but if you divide by the action of the SO2, you just get 1 point. Yeah. Okay. So that's an example of how the slice gives me this local structure, this homomorphism structure, okay, which is an amazing structure. Yeah. Do you have questions or comments on this example, or any feedback?
So this gives you the local structure of the
Yeah.
the graph.
That's me. Exactly. Yeah. The slice gives me the local structure. And the local structure, to understand the local structure, I take this quotient. So the GIT quotient there's one important thing is to remove the non-closed orbits. That's the rule for GIT. That's the rule for GIT quotients. Yeah. Because this kind of a slice is used every time I want to have a local theorem. Yeah. Yeah, you may find a slice. The literature about the slices is kind of weird, I would say, but you will find it in many places. But yeah. But somehow when I was writing things, I needed to rewrite things of slices because I could not find an easy example. Okay. More questions or comments, or I switch to some recalling of group homology and so on that.
Yeah. Okay. That's.
Yeah, that I was using. I'm using here. So let me do some review of group homology. So that's kind of a standard, but that's some things we are using all the time. So we are talking about the first homology group, but in fact we need more homology groups. So first, that was some notation. a vector space V is called a gamma module if there is a representation. So you shouldn't be confused with the representations we are looking at, but because now our favorite vector space is the Lie algebra itself, yeah, V is this one, and the action is the adjoint action. So it acts on the transformations of the matrix. Okay, so I will write it like that way. Is this here? This is something called the bar resolution. I didn't write it, but bar resolution. Just think of cochains. I cochains as maps from I copies. This I is another I, or K or whatever, number of copies of gamma to V. In our case, will be the Lie algebra, maybe. Yeah. And for in dimension 0, this is called the dimension of the cochain space. The dimension 0 is just the space itself. So in this case, it will be just the SLNR. And there is a co-boundary map that, well, I don't need this cool expression. That's something that you can find standard in many books. I just want to use the expression in lower dimensions, 0, 1, and 2, because these are the groups I need. So the first co-boundary is from 0 to 1, yeah, and every element in V or in the Lie algebra just take the action of I map gamma 0 to the gamma 0 of A minus A. Okay, that's something we saw, yeah, when we were talking about B1. Right? The space of co-boundaries will be the image of that. Yeah? But that's more general. That's a particular situation. The other one, delta 1, is this relation which I wrote before, saying that delta 1 equals 0 means that, delta 1 of D equals 0 means the same thing that D belongs to Z1. This is the definition I gave before. And there is a third definition, a third map we need. I don't will really use it, but it's something that we work with. Is this relation, which is kind of longer. Well, it's longer, yeah. And this is wrong. This is wrong. I realize that. No. This is correct. Sorry. Yeah, this is one more time. We have cocycles, it's the kernel, co-boundaries, the image of delta A minus 1. And we saw an example for Z1 and B1. This was the precise definition I gave. And there is the cohomology group, okay? So one important thing that we need one needs for computations and so on is H0. H0 is, because it's something that one can compute. So it's the zero cycles, because there are no zero boundaries, just the zero cycles. If you look at the definition, if this is 0, this is equivalent to say that A equals gamma 0 of A. Yeah. So these are the invariants. Yeah? The invariance means that gamma of V equals V. Well, this A here is a V. Okay, but that's what I'm writing here. Yeah? Because we want to compute Zariski tangent spaces and all this, and this is something with this one is going to be very important, this H0. Yeah? Okay, and I said I was interested in manifolds and orbifolds, so there is an important thing, an important issue, is that when I have a manifold, then this cohomology is the same as the group cohomology, and there is a natural isomorphism. Okay, the standard cohomology with twist coefficient. This stands for the standard cohomology of the well. There are many ways to compute this cohomology with twist coefficients, and this is for instance a bundle. A flat bundle, etc., etc. There are many ways this cohomology can be computed. And I'm also interested in orbifolds, but not any kind of orbifolds, just essentially very good orbifolds, which are quotients of manifolds but a finite subgroup. Okay. I don't know if you are interested in orbifolds too, but well, I might skip this or not. Will this just tell me? So if I have the main idea, there is an important issue is that I could define orbifold cohomology. I will not define that. I will not define it, but it's something standard. The point is that the orbifold cohomology is the same thing as the invariance of the manifold cohomology. So if our orbifold is a quotient of a manifold, I just need to compute the manifold cohomology and take the elements which are invariant, and there is a comma missing here. Okay? So just take everything works for manifolds, and then many things you can translate it into orbifolds, just taking the invariance or whatever, or taking means or so on. So this is not really an issue. You can do it for orbifolds, but don't care. And we have the same thing that for manifolds. If my orbifold is aspherical, means that the universal covering is contractible and very good. So it has a finite covering, which is a manifold. Then the orbifold cohomology is the same as the group cohomology. Yeah. We are interested in compact orientable to orbifolds with negative order characteristic. Yeah? So maybe with boundary or without boundary, which are hyperbolic, which admits hyperbolic metric. And they are all aspherical and very good. When they are not very good, things become complicated. Okay, so if it's for manifolds, it's the same thing that for good manifolds, everything is okay. For orbifolds, you need to work a little bit more, but just take the invariants. And we are interested in the aspherical and very good. And there is something I need to talk about it, sorry, which is a little bit technical, which are the products in cohomology. Yeah. And I work about products in terms of groups. In terms of groups, means we have a cup product. If you are not happy with group, just think of the standard cup product for manifolds. Okay. And there is a standard cup product that goes from if you have coefficients in V1, coefficients in V2, and you get a cup product with coefficients in V1 tensor product with V2. You go from dimension I to dimension J to dimension I plus J. Yeah. And this cup product has some structure. I don't need the precise structures. You can think, if you think of a manifold, it's just a wedge product of forms of the standard cup product. But then I have something else, which is a bilinear pairing, bilinear map from the product. Here I could put the tensor product of two modules to a third module, which is compatible with the action of gamma equivariant. Okay, and this composition defines another cup product. Yeah, just a standard cup product that composed with this. Well, there is a funny notation, which is this one. Yeah, this just means, sorry, the combination of the cup product here with phi. Yeah, so you take two cocycles here or two elements in this cohomology, I get something here. Yeah, and there are two choices we are interested in. There will be more, but the main two are the Lie bracket and the Killing flow. And you'll see why soon. Here is the explicit expression when in dimension 1, but just for cocycles. Yeah, for cocycles, well, you need to work a little bit because it's expression for cocycles and so on, but essentially is the following one. This is Z1 and Z2 are one cocycles. This product is a two cocycle, so it maps. It's a two cochain. Sorry, it's a two cochain. In fact, it's a two cocycle. It maps a pair of elements of the group here to Z1 of alpha, Z2 of beta, but here alpha is acting here. Why is this? Well, that's a standard. You can check it in some group, in some book in any book in group cohomology and so on. So for instance, here there is a book of Brown, which is a classical, and this is explained somewhere. I don't remember which chapter. You can define this expression. The something we'll use that is that well, this phi may be symmetric of skew symmetric. Well, the cup product is the converse. If this is symmetric, this is skew symmetric, and the converse. Okay. Well. And I also have a Poincare duality. Well, there is a Poincare duality. If I take a manifold or an orbifold, which is compact oriented and spherical and very good, if it's a manifold, just think of compact oriented. I have a product from the cohomology dimension I to the cohomology and the cohomology on dimension n-1 relative to the boundary. Well, in the closed case, just forget about this. Okay, but this is something which is a standard into this cohomology with coefficients with R. And what's the pairing here? Which pairing do I use? I use the Killing form. The Killing form goes from the Lie algebra times the Lie algebra to R. And this is not degenerate. This is not degenerate. That's a perfect pairing. And every time I have a perfect pairing and into R, it gives me an isomorphism. Well, B is non-degenerate, and this one is too non-degenerate. It's called a perfect pairing. It has no kernel. So if I take an element here, there is always another element here so that the product does not vanish. And that's very useful for computing, and this Killing form and this pairing with the Killing form gives Poincare duality. Okay. So we'll use this sometime. So what I want to talk for the remaining of the lecture today is these are abstractions to integrability, and this goes with another pairing. And in fact, this is much more complicated. By the way, all this is essentially due to Goldman. There's a paper of Goldman in 1985 that explains in advances. I will give you the reference. I will send you the reference later. So let me start with a representation of gamma into G. I write rho 0 because my idea is to deform the representation, okay? And I write it as a formula for a series of some parameter t. T is a real number or just a parameter. It's polynomial. And I think of polynomials on t. So if I write rho t and as a formation, I would write it that way, using the Lie algebra, the stuff, and so on. So first term is t times a1 of gamma. So for each element gamma of the group, for each element gamma of the group, I take rho 0 of gamma, and then I add a first order term, second order term, third order term, I write a power expansion. And each coefficient lives in the Lie algebra, and I see each coefficient as a map. It's in fact, it's a one cochain. Yeah. To every element of the group, I map it to I of gamma. That's a one cochain. Yeah. It is here. And then if I want this to be a representation, it has to be compatible with the product. Yeah? I could define this just like this, but it has to be a representation. This has to be this product. This has to be satisfied. And the way that people in analytic geometry or just polynomials, they look at this is just look at the power expansion on each term, independent term, coefficient t equal 0 power t squared, t cubed, and so on. Okay? So let me write it that way. I start with the first zero order term. So the first term with t equals 0. This gives me this, yeah. This says that rho 0. Oops, there is a 0 missing here. Is a representation. The first order term, it would be just looking at the term of the first order. And in fact, I don't write it here, but this is the same thing that saying that A1 belongs to the Zariski tangent space is the relation for the cross homomorphism, okay? So which I can write it here if you want, but it's A1 of gamma 1, gamma 2 equals A1 of gamma 1 plus gamma 1 of the adjoint action gamma 2. That's a join of gamma 1. And this action here, well, this is the same thing as saying that delta 1 of A1 equals to 0. This is the same thing. So up to now, we are not writing just what we know. So the point is that what comes next, the coefficient with t squared. Yeah? If we write the coefficient with t squared, I have something like this. This is a cup product. I will not write the precise formula here. Maybe it's a little bit long, but it says that the co-boundary of this guy, yeah, it's the cup product of this guy by itself. Okay, and this is A1. No, sorry, I will not write it, but that's an exercise. It's something that you can work out with all the ingredients I gave. So I say the formula for this. I have a formula for this. You check that if you have this formula and you look at the term of in t squared, the coefficient in t squared, you get this. Okay. So in terms of cohomology, it says that this product is cohomologous to 0. Yeah, this Lie bracket of this cup product of cocycles is cohomologous to 0 because it's the co-boundary of something. And you can continue forever. That's an infinite expression. And in fact, Goldman says that if I have rho t as like this, assume that I can take the development up to the term t to the power of n. Yeah? So it means that it's somebody that lives here. Yeah, this means that I have rho t of gamma is the exponential of t a1 plus plus t to the power of n divided by n factorial gamma a rho 0 of gamma. This is what it means here. So I can go up to the term n. Yeah, okay. Well, in fact, it's written here, sorry. Then there is an abstraction which lives in H2. It vanishes if and only if it can be extended to the next term. Yeah. So let's think what this means. It means that, well, imagine that I have A0, I have rho 0 and A1. When do I have A2? When do I have A2? I have F2 if this is satisfied. So I say that this is the abstraction. Okay. This is the first abstraction. If this is 0, then I can find a term A2. But this you can do it forever. You can continue. If you have A1 and A2, there is a formula that I didn't write here, but it's using the exponential formula and Campbell-Hausdorff and so on. So what Goldman tells me is that if I have A1 and A2, then I have a formula here is A1, A2, whatever. I don't remember. Yeah, if there is something divided by something, there is a third bracket and so on. That's a complicated formula that depends on A1 and A2. So I can define, this is satisfying, I can define a string, and so on and so on and so on. So what does the theorem say? That, well, there is a sequence of abstractions, but it's important to say that I have an abstraction if I have the abstraction n plus 1, if and only if the abstraction up to n vanish. Okay? If the previous abstraction vanishes, I can define the next one. If this abstraction is non-zero, I have to stop. If it's 0, I can't construct and so on and so on and so on. Yeah, that's an abstraction theory. And we will care about the first abstraction. The first abstraction is that for an element of the Zariski tangent space, so it's the first order term, then the cup product, this with itself, so something which lives in here, is the first abstraction. But in fact, all abstractions live here, yeah? So there is the first abstraction to integrability, but there is an infinite sequence and so on, okay? And well, if you want to prove that something is smooth, you have to prove that all obstructions vanish and work a little bit more. Yeah. And the idea is that this will give me an idea of how the singularities look like. Okay. So yeah, I don't know. Do you have questions or comments on these slides? Uh, were you familiar with this obstruction theory, or
Yeah. I mean, I of course read this.
you sure you were, yeah,
Yeah,
probably, yeah. That's very well known. That's something for the
yeah,
85,
yeah.
but it's used it all the time.
Right.
So let me just to finish to show how this is used, because then we'll leave material for the next day,
Yeah.
and we'll review this. Okay. So these are two theorems. The first one, well, two corollaries. The first one is that imagine that we have this situation, yeah, that for some group, for whatever reason, and there are many things where this will happen, this cohomology is zero. Okay. So it can be a manifold or a surface or whatever, which in the next theorem I'll see how this is applied. But if this group is zero, then the variety of representations, not of characters, the variety of representations is smooth. It's not singular and wrong. Yeah. But just the variety of representations. Okay. So as this is just an application of the abstraction theory, I start with a tangent vector, something in the Zariski tangent space. Okay. And I have all this abstraction theory and they live in H2. So what can I say is that all abstractions vanish. Yeah, just because the space where they live is zero. So I have an infinite formal power series. Yeah, I write it like this, and I can write this algebraically forever without caring about convergence. But then there is a very nice theorem of Artin, very important theorem of Artin. It's a little bit, it's from the 60s, I guess. Yeah, that there is also a convergent power series. Yeah. So every tangent vector can be integrated by the vanishing of the abstractions, but by and this theorem of Artin, which is an algebraic theorem. And then, well, in theorem, in fact, it's a theorem in analytic geometry. Yeah. And there is a general theorem that says that, well, if the Zariski tangent space equals the tangent space, then it's smooth. Okay, that's if every tangent vector can be integrated, then it's smooth. I didn't write here, but that's a general theorem. Okay. So all I need to check is that this, if I want to have some space which is smooth, I need to check this and apply Goldman and Artin. So let's do it for surfaces or for compact oriented two orbifolds. Okay, take a two orbifold and take a representation. This is SLNR that is not only reducible but say reducible. So tensor CN tensor, sorry, C tensor Rn, and assume that it's semi-reducible. Well, if it's irreducible, that's very strong. And what Goldman proved in the 85 paper is that this is not singular and wrong. Not only the variety of representations, but the variety of characters. And that the tangent space is more or less, in addition, it's analytic, and in the tangent space, it's the first cohomological. Okay? But we need all this. We need all this theory. So the first thing is that we'll use the previous corollary, of course, because this is why it was here. So the first thing is that, well, since rho is irreducible, you have to prove that the invariants, these are the elements of the Lie algebra, the invariants of the Lie algebra, which are invariant by the action of the representation. You have to prove, you have to start proving this. I'm sorry, I'm lost. And that's not difficult to prove because you have an invariant here, you have an invariant here, and so on, so on. Yeah. And the stabilizer of the orbit by conjugation, this is trivial. Okay, that's a well, I put it as an exercise because I'm lazy, but this is something that you can prove. It's not difficult. It's just some standard. I will look for a reference for that, but something that can be proved. So I claim that this is cohomology 0, so I can apply the cohomology of this group or the orbiful is 0, so that I can apply the previous corollary. Well, there is something very easy, is that if the boundary is non-trivial, then this group is free or it's virtually free, and then if it's virtually free, it has a finite covering. It's either a surface with boundary or has a finite covering, which is a surface with boundary. And well, if has cohomological dimension 1, so H2 is 0. Okay, that's cohomological dimension 1. Oops, sorry. So I don't need to go. It's 0. And then if it's non-zero, and apply Poincare duality, which I said. So a Poincare duality, this group, in fact, it's the dual of this, but I just wrote it like this. Here it would be a dual. Well, the dual of this is this group, and this, well, is isomorphic to the invariant, because it's what I said, that just H0 is the subspace of invariant, and this is 0. This is 0 because it's something that I should have proved at the beginning, because the group is irreducible. So in this case, the space where the abstractions are going to live is 0, so there are no abstractions. So what I said is the corollary tells me that this is smooth at the representation rho, and then I can apply the slash theorem. And the slash theorem tells me that this is homeomorphic to some H1 of a neighborhood in here, yeah, divided by G. But this group is trivial again. This group, yeah, it's written here. Yeah, it's this quotient. Maybe, yeah, sorry. Maybe I'm making a bit mess here. Oops. Yeah, by the slash theorem, what tells me is that this is H1, a neighborhood of the origin in here, of the fundamental group in G here, divided by 0. But this is trivial. And this is trivial, so I have nothing to do. It's this. And in fact, I can use the analytic extractor and so on to this assertion, okay? So that's everything is for good. Everything works well, and we are happy with this. Yeah. And that's what Goldman proved in 85. Yeah, essentially, this is a very nice paper. He proved more things. Yeah, but you have a proof of this of Goldman in 1985. Well, he doesn't need the full power of the slash theorem because he writes this very slides and so on. But I recommend you to go to that paper because he's explaining all these kind of things. Okay. And I think this is a good point to stop.
Yeah, that's right.
It's up to you, if you want. So maybe yeah, it's better if I write things explicitly. So I write. I'm sorry. Let me write. I write a representation. I have a representation rho of gamma, and then I write rho t of gamma. Let me write sometimes exponential of a1 of gamma plus t squared over 2 a2 of gamma plus t squared t cubed over 3 a3 of gamma, and so on and so on. All this by times rho 0. And now I write rho t of gamma 1, gamma 2 equal rho t of gamma 1 times rho of t of gamma 2. Okay, I write it that way. And then I take the power expansions. So on the left, I have 1 times t a1 of gamma times t squared a2 of f2 of gamma. Let me just write up to t squared, yeah? And then I have the square of it is t squared t squared over 2 f2 of gamma, a1, sorry. Well, I didn't prepare this, but essentially that's, let me cheat a little bit. I write this that way, and this, let me write it that way, okay? And then I think I'm done with the second order terms. I have terms with T3. Yeah? Rho 0 of gamma. And now I go to this. Now, okay, I write 1 plus, on the left, I have T of A1, gamma 1, gamma 2. Let me write differently, and let me write alpha and beta. So not to confuse alpha and beta, rho T of alpha times rho T of beta. So I don't confuse the indices. Yeah? I'm very bad for that. So on the left, I have 1 plus T A1, sorry, A1 of alpha beta plus T squared over 2 A2 of alpha beta plus T squared over 2 A1 of alpha beta. And then I have terms of higher order terms that I don't write. All this by rho 0 of alpha beta. This is equal to, I have 1 plus T A1 of alpha plus T squared over 2 A2 of alpha plus T squared. I'm doing something wrong, I'm sure, but F2 of alpha, and same thing for beta. I move this like this, copy, paste, oops, and delete the small one. I put betas here, yeah? Beta, beta, beta. And here it was rho 0 of alpha. Oops, sorry. I move this a little bit more. This is long to write, but it's rho 0 of alpha, and here I have rho 0 of beta. Well, first thing I want to do is to move this guy here, yeah, and take independent terms and so on. So I will get rho 0 of alpha beta with t0. I get rho 0 of alpha beta is rho 0 of alpha times rho 0 of beta. With the first power, I get t1. I get a1 of alpha plus, and now this guy here has moved on the other side. So this is what it's called the adjoint, in fact, adjoint of rho 0 of alpha, a1 of beta. And this is on the right, sorry, I should have put on the left. A1 of alpha beta. And that's a cocycle relation. Then in second order, I get some expression of alpha beta is well, sorry, I will not do the precise computation because it's what I have defined as this one, a1 alpha comma beta. Yeah. I'm sorry. No, it's some expression. Yeah. Sorry. Yeah. Sorry. This expression, let me say it properly, is equivalent to say that delta one of a equals 0. Here I have some other expression that I will not write, but this is equivalent to saying that delta 2 of the second delta 1, sorry, it's always delta 1. Yeah, delta one of this guy is A1 product A1. I could continue and I would get delta one always, sorry, A3 equals, I don't know, something like A1, A2, A1, some combination on A1, A2. Delta one of A3, A4, sorry, with T equals 4 will be the co-boundary of some term, some combination on A1, A2, A3, A4. The point is that this delta one always goes from one change to two chains, co-chains, yeah? So in fact, if you go from here to cocycles to two cocycles, but it's always delta one. Yeah, it's always from here to here. And this condition is always saying that AK is homologous to 0 in yeah, sorry, no, I'm saying wrongly. This is some abstraction, this is some object, this is a two-cocycle, yeah, on alpha and beta, and this lives in Z2. You can check that it's a cocycle. Yeah, it's a two-cochain, but it's also a two-cocycle. And what you can check, and this delta one of AN is a two-cocycle. Yeah, this is the same thing that's saying that the two-cocycle is homologous to 0. It goes to 0 in H2, but it's always in 2. Yeah? It's always in here. So you go to higher order terms, whatever, this is 1, this is 1. This is always a condition on two elements, alpha and beta. So these are just two cocycles, okay? I don't know if this answers this question, but...
Okay, I understand. Thank you.
Yeah, I'm sorry, I'm lost. Yeah. Sorry. Yeah. Yeah, that's something that may be confusing because you go to higher order terms and so on, This has nothing to do. These 2, these 3, they have 4. No, it's always 1 here. Okay? And that's and this is why this group is important.
So is there somewhere we can see that the real computation for some list of computations like
you can see the real computation,
yeah.
and it's not very nice.
Where is it?
But it uses Campbell-Hausdorff formula. There are ways to compute it, and yeah, with Michael Hochner, we wrote this in a paper in the 90s, and there is a typo. We had a but I can look.
Reference to that.
I take in the homework or look for computation. So this
maybe homework.
My homework.
You have to do the homework. Yeah.
This is something I can give you. Yeah, it should be not too difficult for me to find this. I can give you an explicit computation if you wish. Yeah, it's not a problem.
Yeah, it sounds. I never saw the explicit computation, so I'm curious about.
Do you see the explicit? It's essentially Campbell-Hausdorff formula, but it's already explicit computation for that. It's not elementary. I will look for that.
Yeah. Okay.